he didn't teach you how to put on your hairnet?
I don't wear a hairnet.
All right, open your books to 8:23.
How do you know?
It's this is a rather short lesson. It's the short lesson before the beast. Basically, what we're going to be doing here is just kind of talking about some vocabulary and then talking about what a galvanic. I can never say this word. Galvanic cell, I think. I can never say it right. Pronounce it right. And then we'll kind of talk about how it's set up, what it looks like, and then tomorrow we'll like apply some stuff, figure out current flowing through it's essentially a battery, a different version of a battery. But so today is just kind of we're just laying down some vocabulary and the process, what goes on. So 8:23, we're just going to read. Most of it is just basic stuff. So starting on the bottom there, 8:22. Everybody there? I'll wait till everybody's there. Not too fast. 8:23.
No, you didn't.
No, 8:23. Okay, to understand how a redox reaction can be used to generate a current, do you guys know what current is? I know you definitely should. You guys know what current is? The flow of electrons. Okay, current is how much charge flows per unit time. Okay, that's what current is. It's probably pretty important to know what that is. If you haven't taken physics, then it's understandable that you probably don't know the definition of it, but it is the rate at which charged particles flow. All right? Let's consider the reaction below. And I think that is one of the reactions we did yesterday in class. In this reaction, iron is oxidized and MnO4 is reduced. Electrons are transferred from the iron to the MnO4. It is useful to break the redox reaction into half reactions, one involving oxidation and one involving reduction. So you can see the reduction reaction there, half reaction, and the oxidation, half reaction. Okay? The multiplication of the second half reaction by 5 indicates that this reaction must occur 5 times for each of the first reaction occurs. The balanced overall reaction is the sum of the two half reactions. Flip the page. Nothing new, just kind of piggybacking off what we did yesterday. We did that actual reaction yesterday. Okay? When MnO4 minus and iron are present in the same solution, electrons are transferred directly when the reactants collide. So what they're saying is if I had those two ions in the same solution, when they would collide, they would just transfer their electrons directly to each other. Okay? Under these conditions, no useful work is obtained from the chemical energy involved in the reaction, which instead is released as heat. So basically, if they transfer the electrons directly, what are you doing, Rylan?
Trying to manage her. She's panicking because I'm so practically close to freezer. Sorry.
Sorry, that's pretty funny.
It wasn't really important for you, thankfully, but she's panicking because there's focus on the job.
Was it yours?
No. But she's asking me if someone else didn't do the job.
And how would you know?
I wouldn't. I'm kind of telling her that right now.
Ooh, that's a little over the top. All right.
I've never done it before.
There you go. I'm sorry. That was so dumb. Okay. Where was I? Okay, so what I was saying is if these two ions are in the same solution, they will just collide, transfer their electrons, and there's really no way of using that chemical energy. It just gets dissipated in the form of what? What did they say? Starts with an H, ends with an eat. Okay. Alright, got it. Good job, guys. I'm so glad you guys are on top of this today. Alright. How can we harness this energy then? The key is to separate the oxidizing agent from the producing agent, thus requiring electrons to transfer through a what? Wire. Now, do you see the little picture up top? Are you engaged? I know Ryland has to deal with a minor catastrophe. A freezer was left open.
It was an empty freezer.
What?
But it was like a miniature portable one that was going to cost power. So just trying to figure out who's responsible for that. Exactly.
One grand. Alright.
Even the guy you don't know at all. It's that guy's fault.
Alright. So, if you put them in two different solutions and connect a wire to those two solutions, electrons, believe it or not, will transfer through the wire to the other solution and cause the redox reaction to happen. To me, I think that's pretty cool. The current produced in the wire by the electron flow can then be directed through a device. What do you think they mean when they say through a device? Okay, a wire would be how... Yeah, when they say device, they're saying using the electrical energy to do something, like you could connect it to a light bulb and cause the light bulb to light up. Does that make sense? That would be an example of a device. Basically, what they're saying is if you do it this way, you can basically take the electrical energy that came from the chemical energy to do work on something. Okay? To power something. Use the electrical energy to do something. Okay? Such as an electric motor to provide useful work. For example, consider the system above. If our reasoning has been correct, electrons should flow through the wire from the iron to the MnO4. However, when we construct the apparatus as shown, no flow of electrons is apparent. Why? Careful observations show that when we connect the wires from the two compartments, current flows for an instant and then stops. The current stops flowing because the charge built up, because of the charge built up in the two compartments. So what they're saying is it starts to flow for a period of time. Electrons from one side will flow to the other side. However, when that happens, you're going to see charge buildup. Right? You're going to start seeing one side becoming more positive and the other side becoming more negative, right? Okay? Well, when you start doing that, you're starting to create a lot of potential energy, which is going to oppose that flow. Does that make sense, everybody? Okay? If the electrons flow from the right to the left compartment in the apparatus shown, the left compartment receives electrons who become negatively charged, and the right compartment would become positively charged. Creating a charge separation of this type requires a large amount of energy. In order to get the electrons, or to get the charges to be displaced that much, it would require work and a lot of energy. Thus, sustained electron flow cannot occur under these conditions. So let me go and talk about how they fix this problem. However, we can solve this problem very simply. The solution must be connected so that ions can flow to keep the net charge in each compartment zero. Okay? So what they're saying is, if you could do something to allow ions to flow from one to the other, so that when electrons are going through the wire and making it charged, it's reducing its charge by allowing ions to flow through. So you still have the electrons that are flowing through the wire, which are doing work in the form of electrical energy. At the same time, allowing ions to flow from one solution to the other will cause the charge to stay at zero. Right? So if I were to do a little visual up here, and that's what I'm just going to talk about it here in a sec. They'll use what's either called a salt bridge or a semi-permeable membrane. So there's your wire. This is what's called your salt bridge, and what is in that is like a jello-like mixture of ions, electrolyte solution, that as electrons are flowing this way, electrons in here, or ions that are negatively charged in here, are flowing that way. Right? Because as this starts to build up and become more negatively charged, it's not going to repel the negative ions in here, in this little tube. Does that make sense, everybody? Okay? So what it's going to do is it's going to start repelling the negative ions in the tube into here, and be attracting the positive ions in the tube into here, thus keeping both sides relatively neutral. Does that make sense? Okay? So you still have the electrons flowing, which can do work, can be used to generate power of some sort, while at the same time keeping it going because you're not getting a huge charge displacement. Okay? The solutions must be connected so that the ions can flow to keep the net charge in each compartment zero. This connection might involve a salt bridge, and that's what I was showing you there, or a porous disc in the tube connecting the two solutions. Either of these devices allows ions to flow without extensive mixing of the solutions. You wouldn't want them to mix too much, otherwise you defeated the purpose of wanting electrons to go through a wire. Right? When we make this provision for ion flow, the circuit is complete. Getting a phone call. Okay. Electrons flow through the wire from the reducing agent to the oxidizing agent. The ions flow from one compartment to the other to keep the net charge zero. That's what I stated earlier. We now have covered all the essential characteristics of a galvanic.
Galvanic.
There we go. Galvanic. It's been like 4 years since I talked about this. All right. Where was that? The reaction. So a galvanic is a device in which chemical energy is changed to electrical energy. Okay. I don't know if we've talked about this, but a battery, those batteries that you use to power a flashlight or whatever you use a battery for whatever purpose, what that is a chemical energy being converted to electrical energy to do work. Okay? So what we're seeing here with this is basically a form of a battery. Does that make sense? Taking chemical energy, the energy stored up in the ions, okay, through the redox reaction, is producing now electrical energy in the form of electrons flowing. Okay? So that we can use that energy that was originally stored up in the chemicals to be taken out of there, transferred to electrical energy, and being used to do work of some kind. Okay? The reaction in an electrochemical cell occurs at the interface between the electrode and the solution where the electron transfer occurs. So you have two different types of electrodes, and you've probably heard them before, or at least their names. Which is a anode and a cathode. Now I have generally, I struggled to remember which was which for the longest time. One thing that helped me, although it's not that earth-shattering, but it helped me remember which one was the anode, which one was the cathode. Oxidation happens at the anode, and reduction happens at the cathode. And this has no A and this has no C.
Or they're both consonants, so consonant, or a vowel with vowel.
That's another good way of remembering. Good job. Okay, I just have had in the past a difficult time remembering what happens at the cathode. Okay, reduction happens at the cathode. what happens at the anode? Oxidation does. Okay? You're going to need to be able to know that because we are going to have to set up our own cells eventually, and that's what we'll start doing tomorrow. We'll set up our own, and we want to figure out, not tomorrow, Monday, yeah. Thankfully it's a week. Holiday. It's a long week. For me. I don't know about you. I don't know about for you guys. Okay? So, anode and cathode. Just some vocab here then, like I said. These are our two things that can be used to, what are these, what did I say the purpose of these was? Transfer what? Ion. Why would we need to transfer ions in this galvanic cell?
Keep the electrons flowing.
Keep the net charge of? Yeah, to keep the electrons flowing because, right, if electrons are flowing, you start to see a big charge displacement, right? A lot of negatives on one side, a lot of positives on the other side.
Yeah.
Okay? So in order to keep the charge flowing, you have to have some apparatus that allows ions to make the charge stay neutral. So as negatives are coming across one way, they're going the other way in the form of a different kind of ion. What's that?
How does it like go on this?
It's not like a hollow tube. It's like a jello-like substance in here. Yeah. Kind of the visual looks kind of deceiving, but it's not like a hollow tube. Okay. So last thing, and we're almost done. Last couple paragraphs here. A galvanic cell consists of an oxidizing agent in one compartment that pulls electrons through a wire from a reducing agent in the other compartment. Right? The pull or driving force of the electrons is called the cell potential. Now again, the only one who probably knows what potential difference is or cell potential is Emily to physics. Right? Cell potential is basically your difference in your potential energy of your two compartments. Okay? And it's used, or its unit, you probably are familiar with the unit, is a volt. You probably heard that unit before. Okay? Basically what that is the joule of work that can be done by a coulomb of charge transfer. Okay? It's kind of a word, but how can we measure a cell potential? One possible instrument is a crude voltmeter, which works by drawing current through a known resistance. However, when current flows through a wire, the frictional heating that occurs wastes some of its potentially useful energy. So what they're saying is, if I want to know the potential difference of this battery, if you will, because this is a form of a battery, okay, I could put a voltmeter up on it. The only problem is as electrons are flowing, they actually will start to lose some of their energy due to electrons' friction going through the wire. So what he's saying, what this book is saying is, when I use a voltmeter, the potential difference or the volts that I see on the voltmeter will be less than the actual source. Okay? Because some of it gets lost in the form of what? Some of the energy gets lost in the form of what? Okay, as a result of friction. Yep. Okay. So a traditional voltmeter will therefore measure a potential that is less than the maximum cell potential. The key to determining the maximum potential is to do the measurements under conditions of zero current. If you don't have current flowing, you won't have any friction or resistance or energy loss. Does that make sense? Okay? So that no energy is wasted. Traditionally, this has been accomplished by inserting a variable voltage device in opposition to the cell potential. The voltage of this instrument, which is called a potentiometer, is adjusted until no current flows. Basically what they do is this potentiometer resists the flow of the electrons to the point where they stop. Okay? So it has to have enough potential difference of its own to be able to stop the potential difference of the cell. Okay? Under such conditions, the cell potential is equal in magnitude, but what in charge? Opposite. Okay? Opposite in sign to the voltage setting on the potentiometer. This value represents the maximum cell potential. It then goes on to talk about how they don't really use potentiometers anymore because modern technology has gotten to the point where if they use a voltmeter or a device that just measures the volts, they've been able to do it so that the resistance is so little because the current is so little. So the advances has allowed them to use a traditional voltmeter. But we will do mathematical calculations of the potential difference of a cell, a galvanic cell that we have shown here. And that's what we'll start doing on Monday, excuse me. We'll start doing finding the cell potential of a particular galvanic cell, predicting a few things, using them